So today we'll be talking about minimum spanning trees in the first part of the lecture. Then in the second part of the lecture we will be talking about shortest paths algorithms with negative weight edges. So in the second part we will be doing single source shortest paths with negative edge weights. But in the first part we'll be doing minimum spanning trees. So last time we I gave a brief introduction to minimum spanning trees. So a minimum spanning tree is just you are given a weighted undirected graph. So the input is a weighted undirected graph. The graph is weighted and undirected. And in general, if you have a graph, in general the number of edges, if it's an undirected graph, it can have up to v minus 1 by 2 edges. So the maximum number of edges that it can have is v times v minus 1 divided by 2. This is what a complete graph has. Now, in the minimum spanning tree problem, the objective is to select a tree, which is a subset of the graph, a subset of the edges. How many vertices will the tree have?
All of them.
How many vertices will the tree have? A tree always has v minus 1. E tree is always v minus 1. No matter what, a tree will always have v minus 1 edges. So the minimum spanning tree problem is selecting v minus 1 out of this, the total number of edges, which can be up to v minus 1 divided by 2. So we want to select these edges such that all the vertices are connected and the sum of weights of the edges that we have selected is as small as possible. Okay? So when I get them connected, in order to connect v vertices, we need at least v minus 1 edges. Because remember, a tree connects vertices using the minimum number of edges, which is v minus 1. It's impossible to connect v vertices with less than v minus 1 edges. That's the minimum that you need. Okay, so in terms of the number of edges. Now in the minimum spanning tree problem, each edge has a weight, and we would like to select a subset of these edges that form a tree and connect the vertices such that the sum of edge weights is as small as possible. Now having said that, this is the minimum spanning tree for a weighted undirected graph. Now what about the minimum spanning tree in an unweighted graph? If I give you an unweighted graph, what's the minimum spanning tree?
Any tree. Any tree could be.
Okay, any tree that connects all the edges, right? So all trees, if it's unweighted, then every edge will have a weight of 1. Then if there is a tree that connects all edges, then any of such tree will be a minimum spanning tree. Right. Now, how do we find such a tree? How do we find such a tree?
BFS?
Yeah, so just do any traversal. So you can do BFS or DFS to find any tree. Because BFS and DFS, they form a tree. They select a subset of the edges that connect the vertices if possible. So if you have vertices like this, okay, you will find a tree that connects them. But if you have vertices like this that are disconnected, there is no tree. There is no tree that connects all of them. So there is no spanning tree for a set of vertices that are disconnected. You can find a minimum spanning tree only if the vertices are connected. Okay? So now this is the example that we will be using to illustrate the algorithm, which is Prim's algorithm. Now, Prim's algorithm, it's a greedy algorithm. And it's very similar to Dijkstra's algorithm. Now, remember, the main difference between the shortest paths problem and the minimum spanning tree problem is that in the shortest paths problem, we talk about paths. So in Dijkstra, we talk about paths. We have the notion of a path. In Prim's algorithm, we don't have the notion of a path. We have the notion of a link. So a path is a sequence of links, right? But in Prim's, we only care about links. All what we care about is linking these vertices together. And we don't have the notion of a path. Remember the example that we gave last time? If you have vertices like this, A, B, C, D, and you have 1, 2, 3, 4, 5 edges, then the minimum spanning tree in this case, the minimum spanning tree is going to be this edge, and this edge, and this edge. So this is a tree that connects all vertices, and it has the minimum sum of weights. So this is the minimum spanning tree. Now, this minimum spanning tree does not give the shortest paths between the different vertices. For example, does not give the shortest path between A and D. Right? The shortest path between A and D is this. While if we go, the shortest path that is based on the minimum spanning tree is 1 plus 2 plus 3, so that's 6. Okay. So in the minimum spanning tree, we don't have the notion of a path.
What would be an application of Prim's algorithm? Why are we calculating just this minimum link weight, for example?
Okay. So who can answer this question? So we answered this question last time.
A social network.
What was the question?
Any kind of network.
Application.
Any kind of network. So you are given a number of vertices, and we would like to connect them using the minimum cost. So these could be computers that you are trying to connect using minimum wiring, the minimum wiring cost. So we don't care about the path between computer A and computer B. What we care about is the sum of costs of the wires that we use to connect the computers. Okay? So our objective is not minimizing a path. Our objective is minimizing the sum of edge weights, or the sum of costs of the wires that we use to connect the computers. In fact, later this semester we will be doing some kind of application type of questions on graph algorithms and different algorithms. So to illustrate, what we can, what's the use of each algorithm. Okay. So now let's do this example. Now, with minimum spanning trees, you can select any vertex as your source. So you can start from any vertex, and you will always discover the same minimum spanning tree. So let's now, arbitrarily select just A. Okay, and the algorithm will be very similar to Dijkstra. So we're going to put all the vertices in a priority queue. So we're going to put all of them A, B, C, D, E, F in a priority queue. And we will have, for each vertex, we will have the current key, which is the cost of the link. It's a link cost. Remember, it's a link cost, not a path cost. So it's the cost of a single edge that connects the vertex to the rest of the network. Okay, it's the cost of a single edge or link that connects each vertex to the rest of the network. So since we have chosen this as a source, this is going to have a key of 0, and everything else will start with infinity. And then we'll have the notion of the parent again. And initially it's null. So it's a greedy algorithm. So we're going to say, okay, now we started with A. A is connected. It's linked to the network. We only have one node in the network at this point. Now what's the next logical step is to look at the neighbors, right, to see if we can link one of them. So we have 3 neighbors, C, D, and B. So now we have discovered a way of linking D, and that will cost us 4. So for D, we have discovered a way of linking D with cost 4, and this is going to come via A. So we're saying now we have an option of linking D using this edge, linking D to the network using this edge, and this will cost us 4. And we can link C to the network with a cost of 9. And again, the parent is going to be A. And we can link B to the network with a cost of 6. And the parent is going to be A. Now, what's the logical greedy choice? Yeah, so link D. So basically, I'm trying to connect these vertices together. And now I have a set of connected vertices which initially has only A. And these vertices that can be connected now to A, the 3 vertices that can be connected to A, this is the lightest edge, the edge with the minimum cost. And so I will greedily select D and connect it. That's my greedy choice. And I will connect now. I will have a network now that has A and D both connected. Now, do you have any doubt that this is the minimum spanning tree that includes A and one of its neighbors? Or in fact, that includes A and any other vertex? So can there be a better, a lower cost tree that includes A plus another vertex? No, because the only 3 vertices that can be connected to A are D, C, and D, and the lowest cost is connecting D. So now I have, this is you can think of this as a minimum, as a subtree, as a minimum subtree, spanning subtree that includes A and D. And in fact, I will keep growing the tree using the same greedy choice. Each time I have multiple options, so I just pick the link, that the lowest cost link that will connect one of the unconnected vertices to the network that I'm growing, or to the tree that I'm growing. But now what's the logical thing? I have decided to add D. So now D is done and A is done. Now what should I do with D?
Neighbors of D.
Yeah, exactly. Look at the neighbors. Look at the neighbors of D and see if I can connect one of them. Now, see that now the neighbors, the remaining vertices that are not connected yet, now they can be connected either to A or to D. Now, in my priority queue, I will be keeping track of the cheapest way of connecting each vertex. So the cheapest way could be either connecting to D or connecting to A, because currently the only 2 vertices that are in are A and D. Okay, and so I will now find by looking at the neighbors of D, I will find the cheapest way of connecting each vertex. At this point, I only have only two ways, either by connecting it to A or connecting it to D. But then as I add more vertices to the minimum spanning tree, there will be a third and fourth and fifth option and so on. Okay, so now I look at the neighbors of D. C, now I can connect C with a cost of 8. So I have just discovered a better way of connecting C. So this is going to be 8, and it's going to be through D. Now I will look at, in fact, I will look at A, but I will realize that A is already in. So I only consider the neighbors that have not been connected yet. There is no point in considering the neighbors that have been connected. Then I look at F. Now I have just discovered a way of connecting F with a cost of 2. And F is the parent is D. So by adding D to the network, I have more options for connecting the remaining vertices. And each vertex, each of the remaining vertices now has the better of the two options. Of course, some vertices have no option. Still, E has not been reached yet, so that I still don't have any option for connecting E. I will get to it at some point later in this algorithm. Okay. So now, what's the next step?
Yeah.
Connect F.
Yeah. Look at F. Why F? Yeah, it's the lowest cost. So look at F. Now I have, I can connect B with a cost of 6. I can connect C with a cost of 8. I cannot connect E. I can connect F with a cost of 2. So I'll go for the lowest cost. It's a greedy algorithm. So I will connect F with the lowest cost, and I will pick this edge. Okay. Now F is done. Now what's the next step? Yeah, exactly. Check the neighbors of F, and I only care about the unconnected neighbors. And there is C. So now I can connect C with a cost of 5. So see, I keep discovering better or cheaper ways of connecting vertices. So I have just discovered a better way of connecting C with cost 5. And the parent is F. Okay. So at any point in time, you have connected a subset of the vertices. So at this point, the connected subset has 3 vertices. So we have no doubt that what we have connected, is the best. We couldn't have done any better than this. We have connected these 3 vertices, and this is the best way of connecting these vertices. Now we are looking for a way of connecting the rest of the vertices to them, and each one of the remaining vertices can have up to 3 possible edges: an edge to A, an edge to D, and an edge to F. Not all of them will have all 3 edges, but they can have up to 3 edges, and we'll just pick the lowest cost edge to do to connect a vertex. Okay. So in this case, for Prim's algorithm, we're not going to do a formal proof for this, so I will let you read the proof in the book. But this is the intuition behind the proof. This is the intuitive idea, is that you always have a subset of the vertices that are connected, and you are trying to connect one of the remaining vertices, and there is no better way of connecting one of the remaining vertices. There is no way better than choosing the cheapest edge that that connects the set of unconnected vertices B, C, and E to A, D, and F, or one vertex from this set, to the minimum spanning tree, or the partial minimum or subtree that I have grown. Okay. Okay, so now we updated the neighbors of F. Now with what is remaining, I have 5 and 6, so I go for the 5. So I go for the 5, and then I update the neighbors of C that have not been connected yet. So I don't update A because it's connected. I don't update D because it's connected. I only update B and E. So B will get updated to 3, and the parent is C, and E will get updated to 7, with the parent being C. Okay. Now C is done. Now I'm left with 2 vertices, B with 3 and E with 7. Which one should I B? So the greedy choice is B. And I will update the neighbors of B. So connected, no update is necessary. Connected, no update is necessary. And E, should I update E to 10?
No, because we already have a better solution.
Yeah, exactly. So we already have 7. So we update only if we discover a better solution. So what we keep track here is the best option that we have. And this is an additional option, but it's not better than the options that we had previously. So we don't update here. So B is in, and last step is connecting E. We will connect it using the 7, the cheapest option for connecting the E. So this is our minimum spanning tree. This is a tree selecting V minus 1 edges to connect the vertices, and the sum is as small as possible. So in order, let's draw this as a tree. So our minimum spanning tree will look like this. We have the A, then the child is D, then the child of D is F, and the child of F is C, and the children of C are B and E. Okay. Okay, so any question about the algorithm? Yeah.
So when we're selecting the minimum, how do we tell you when something is already a link? Is that just a flag that we're setting a mark?
Okay, that's a good question. So an easy way of implementing this is just putting a field, a flag or data field in each vertex indicating whether it's connected or not. So initially all vertices are not connected. Then at some point they will get connected. So just have a field in each vertex. Yes?
So in the algorithm, we start at A and then we check B, C, and D to see which one has the minimum link. And then we sort of go to D and then we check again from D. So we check C and F.
Mm-hmm.
Okay.
Yes.
So then at one point from C, when we're at C, wouldn't we go to D and then check A and E? And
Yeah.
then go to E?
Yeah, so when we added C to the minimum spanning tree, we checked on all the vertices, but we skipped the ones that are already connected.
So B and E were not connected at that point, right?
Yeah, so B and E were not connected at that point. So these were the only ones that we updated. But the ones that were connected, we just skipped them because they have been connected already.
But wouldn't B check E and then it would make E so then it would make B the parent of E, but then it would go to E and then E would check. I'm confused about how it sort of selects E. Like, wouldn't it select it first from B and then overwrite it? Or?
Well, when we were at C, so let's, okay. When we were at C, the neighbors of C are A, D, F, E. Well, everyone is a neighbor of C. All vertices are neighbors of C. So we skip the neighbors that are connected. So we skip A, D, and F. And we look at the neighbors that are not connected. So we look at B and E. So we update B to 3 and E to 7. Okay? Then it's in the priority queue. Then the next step, we don't look at the neighbors now. After updating the neighbors, we look at the priority queue, because the last update that we did not necessarily give the best solutions, right? So our choice is not based on the last update. It's based on the best update that we are tracking in the priority queue. So the priority queue tracks the best choice that we have for each vertex. And the best choice for each vertex is not necessarily the last, the last update that we did, or not the update, the check, or the last link that we have discovered. The last link that we have discovered is not necessarily the best link. Okay, so that's why after we just do the updates, we go back to the priority queue and see what's the best for each vertex.
Initially, everything's in the priority queue. So we grab the first one that's non-infinity.
Yeah, initially everything is in the priority queue. Okay. Okay, any questions? So let's write the code. In fact, the code is very, very, very similar to Dijkstra's algorithm. The only difference is that we're talking about edge weights instead of talking about paths. So the prim of G, first of all, for each, or let's first select the source. U dot key equals infinity, and U dot pi equals null. Okay? Then S dot key equals 0. Then we create a priority queue Q. Then for each vertex U, we do Q dot insert of U. So far the same as Dijkstra. Then while Q is not empty, what we do is U equals Q dot extract minimum. Okay, and then we go through the neighbors. For each neighbor, V of U, what we do is, now if, first of all, we have to check if it's in the priority queue or in the minimum spanning tree. So if it's not in the minimum spanning tree, if it's still in the priority queue, if V belongs to the queue, if V belongs to the queue, and what? What's the condition that we check? So what were we checking here? When we were updating? Okay, the cost of what? What were we comparing? So we were comparing the current link weight with the best. Okay, so the weight of the edge UV. So if weight of edge UV is better than the current key of V or key of U? key of V. We're checking on the neighbors. So we're updating the key of the neighbor. So it's V dot key. Then V dot key equals what?
Is weight of U.
Weight of U.
Yeah, weight of U and V. And the parent V dot pi equals U. By the way, a correction, when we did Dijkstra, we did not, there was an error. We did not do this update of the parent in the if statement. So the update of the parent is, was it? Oh, it was in the if statement. I think the first time, I think. Well, I think I wrote it twice. So the second time was correct, but the first time it was not correct. It was outside. So it should be inside the if statement. Okay, so we update the parent. Yeah. So if you have it written twice, I think the first time wasn't right. The second time was right. But the right thing is to do the update of the parent only if the condition is true. Okay? So now this is the code. Well, and in terms of analysis, what do you think?
The same as Dijkstra.
It's exactly the same. Yeah, exactly the same. In fact, we have here V times inserts, and here we have V times extract minimum, and here we have E decrease key. So it's identical to Dijkstra's analysis. In fact, the only difference between the two algorithms is this. So here, in Dijkstra, we compare and update paths. Here, we compare and update edges, single edges. Okay? In Dijkstra, we compare and update paths. Here, we compare and update single edges. Okay, so this is Prim's algorithm for minimum spanning tree. Any questions? Yeah.
So in the second part of the reinsert,